Now we are going to discuss the open delta connection. So the delta connected winding, this is going to be like this, right? Now what happens if one of the phases is, for some reason it is faulty or it has been removed? Then what is going to happen? We are still going to get 3-phase output even if one of the phases is removed. That is the significance of the open delta connection. This is the normal delta transformer. Now what will happen if one of the phases is removed? This phase cannot get excited, right? Because it is going to get induced voltage if this is excited. If there is no if there is no winding here, then this will also not have any, it will not deliver any voltage. So this will be the open delta connection. So it is shaped in the form of V. So sometimes it is also called as the V connected transformer. If you take these lines as A, B, C, and on the other side you have A, B and C. Now this supply, this input you are getting, this is a normal 3-phase balanced supply. So what will be the voltage across this winding? It is going to be VAB, and across this winding is going to be VCA. And what about the voltage between the terminals B and C? Even if there is no winding here, you can still find out the voltage between the terminals B and C, right? So if you take this terminal as positive and this is VBC, this is negative. So VBC is going to be minus of VAB and VCA, right? That means VBC is equal to minus of VAB plus VCA. If you are applying the KVL, you are encountering the negative sign first. Now how can you represent VAB? So if you take the magnitude as V and the angle as 0 degrees, then VCA is going to be V angle 120 degrees. This if you calculate, you are going to get V angle minus 120 degrees. So you can see that VAB, VBC and VCA, they will still form a balanced 3-phase supply. It is having the same magnitude and they are all each 120 degrees out of phase. And now the same voltages are going to be induced here. So here this is wrong representation, right? This is going to be the B terminal. This is going to be B and this is going to be C. So now you have voltages VAB here and this is going to be VBC and this is going to be VCA. You can mark the dot convention as well. Here there will be one dot, here there is one dot, here there is the dot and here there is the dot. So voltages form a 3-phase supply. Now what about the currents? In a similar way, if you take this as IA, IB and IC. So you can see here that IA is still equal to minus of IB plus IC, just like in the 3-phase balanced system. So in this way the current relationships also you can verify that they are indeed satisfying the 3-phase balanced system relations. So you can write thus the line voltages and currents. Remember, line voltages and currents, not the phase quantities, only the line quantities, are going to form a 3-phase balanced system, even if one of the windings is absent. Even if one winding is absent. This is the open delta connection. So one thing that you have to note here is these all form a 3-phase system, that is well and good, but the magnitude that is going to be present, this is going to be different from the original magnitude. So the power is going to differ. Now the total power cannot be delivered, only some part of the power can be delivered. So what is that amount of power? Power delivered in open delta connection. So in order to find this, we will first consider a normal delta transformer. So here we have terminals A, B and C, and here we have A, B and C. The dot also you can take, right? This is the dot convention. Now the output line currents, if you take as IA, IB and IC, they are all going to form a 3-phase system. So we will first draw with IA as the reference. So this is IB and IC. Now what about the phase currents? If this current is IAB, this is going to be IBC and this is going to be ICA. Now if you represent the phase currents in the phasor diagram, this is IA plus of minus IB, this is IB, and here you are going to get minus IB. If you add both these vectors, you are going to get IAB, and we already know the magnitude of IAB, which is the phase current, is going to be less than the line current. And what about this? This is going to be 30 degrees. Now let us say the load power factor is given by cos phi, lagging. Then it means that the phase voltage is going to lead the current by 5 degrees, or you can say current will lag by 5 degrees. So the phase voltage we will draw here, this is going to be VAB. Here phase and line voltages are one and the same for delta connection. So this is phi. Now here note that the phase difference between the voltage and the line current, it is going to be phi plus 30. Now similarly you can draw the other voltages. The phase relationship is phi plus 30, and this is also going to be phi plus 30. So this is VBC and this is VCA. Now what is the power that is delivered here? P of delta delta transformer is 3 times V phase I phase cos phi. Now we will see the delta connection. Here we have removed the BC winding. Now if you consider the phasor diagram, the currents, the line currents IA, IB and IC, they are going to remain as it is, the phase relationship, okay, and the voltages as well. So what was the phase difference between the voltages and the currents? We saw that it was phi plus 30, okay. So now this is VAB, and here you are going to have VBC, and here you are going to have VCA. So each of this is phi plus 30, and similarly this is phi plus 30. Now what will be the power in the VV connection? Okay, so open delta we will represent as VV. So this is going to be, this is one transformer, this is the other transformer. So the voltage and the current across it into the cos of angle between those voltage and current. So what is the current through this winding? If you take this winding, first we will take this winding, this is first winding and this is second winding. So what will be the power delivered by the first winding? This is the magnitude of current IAB into the voltages VAB, and now what is the phase between IAB and VAB? So you can see that IAB is nothing but simply minus of IB. So you can represent this in the phasor diagram. This is going to be minus IB, which is IAB. Now what is the phase between this voltage VAB and IAB? So this is angle 180 degrees, this is 120. So what is this angle? It is going to be 60. Now this angle is phi plus 30. So what is this left out angle? This is going to be 30 minus phi. So here you have cos of 30 minus phi. This is the first transformer. What about the second transformer? The voltage across this is VCA and the current is ICA. So if you write ICA mod VCA, and what is the phase between these two? Now ICA is simply equal to IC. So this is IC in the phasor diagram and VCA is here. What is the phase between them? Phi plus 30. So you are going to get cos of 30 plus phi. So now what is this? Mod IAB is nothing but the phase current. The phase current, that is the current that is delivered by each of the winding, will remain the same, right? The capacity of the winding. So IAB, mod IAB is I phase. And what about mod VAB? That is also V phase. So V phase, I phase cos 30 minus phi. Similarly, ICA is the phase current and VCA is the phase voltage, cos of 30 plus phi. So here cos A plus B formulas and cos A minus B here, if you apply trigonometric relationships, the final answer you are going to get root 3 times V phase I phase cos phi. So for delta delta, what was the power? This was 3 times V phase, I phase, cos phi. So this means that in open delta connection only 1 by root 3 times of the power is delivered. So this is nothing but in terms of percentage you are going to get 57.7%. Okay, so just because one winding is removed, 2 by 3 of the power will not be delivered. 2 by 3 is 66.66%, right? So still lesser than that power is going to be delivered. Only 57.7% of power is going to be delivered in an open delta connection.